So this paper will act as a work in progress review of the work I'm conducting as part of my MA Archaeology dissertation, supervised by Dr. Kamal Badrashani. I intend to outline the methodology for materials analysis, which I'm currently using to process the material for the excavation conducted at Binchester Roman Fort by Durham University and Durham Archaeological Services. This will have the broader ambition of examining some of the possible differences between glass quality, form, and composition between the fort and the extramural settlement external to the fort, if there are indeed any. This could then be used to explore the possible use of glass as a proxy for measuring and discussing social differentiation across sites and areas. Due to its status as an imported item, the glass trade contextualizes Binchester and the wider northern Roman Britain area in both a regional and empire-wide trade. The complexity of Romano-British glass recycling adds an element of complication to the study, which will also be examined in brief. The examination of the glass material from Binchester Roman Fort will, eventually, form part of a much wider geochemical study into glass consumption in fort/extramural settlement complexes in northern Roman Britain. This will hope to shed light on the possibility of the use of glass as a proxy to highlight any variations in wealth across forts and extramural settlements, and how these shift over time with the changing usage of forts and extramural settlements. With this in mind, this paper will focus on the sampling and preparation methodology I will be using in this study, and how these techniques have the potential for providing high-quality results. To start, a brief but important chemistry lesson. So, as you can see from the diagram, glass is essentially a descriptor of state, meaning any non-crystalline solid, as we can see from this atomic diagram. In the most simplistic terms, it's a mixture of a silica source and an alkali, which when heated to a high temperature forms a substance that is plastic, so meaning in this case formable into shapes when hot, but hard and brittle when cools, and can hold amorphous shapes. So, ancient glass is predominantly made from 4 ingredients, although there will be some significant exceptions that will be discussed later on in this talk. Silica, which is the main structural component of glass and is found in sand, crushed quartz, or feldspar. Quartz is, of course, a natural building block of ancient glass due to its durability, as it actually has a higher melting point than steel. Flux, which is the alkali needing to lower the melting temperature of the sand or quartz, which is crucial because silica begins to melt at 1700 degrees C. By lowering the natural temperature of silica, this then disrupts the chemical structure of the silica to form a lattice, as we can see previously, with the stabilizer and the colorants. Plant ash and potash could also be used, but natron is predominantly used in Roman glass. And then there's lime, which is obviously calcium carbonate, to strengthen the glass, acting as a stabilizer for the silica. And in this case, it's often limestone. Colorants can then be added to change the color of the glass, but some of these also have an impact on the chemical composition, and therefore structure, tensile strength, and durability. The colors are formed from the light passing through the glass interacting with the metal ions embedded in the matrix of the glass material through a process known as ligand field theory. These are often transition metals, which can be found slap bang in the middle of the periodic table. One of the most commonly found colorant in Romano-British glass is copper, which can be combined with cobalt to create a vivid bright blue, and lead to create emerald green. Antimony can be used to form opaque glassware, which also reduces the iron content, which naturally creates a sort of pale green-blue color, as you can see on the slide from one of my photographs, which can then be added in extremely high concentrations. So, recycling is a bit of an issue, but it is perhaps a controversial statement to suggest that the majority of glass material found in Roman Britain for the first half of the first millennium came from factories in the Levant, either as full vessels, raw glass, or cullet. The full vessels would be supplied to consumers, and the cullet and raw glass would be worked in smaller localized factories. Full vessels could then be recycled as cullet, then fed back into the domestic glass market via itinerant glass collectors and traders thought to operate in the province, as per Chloe Duckworth and Andrew Wilson's publication, Recycling and Reuse in the Roman Economy, and Victoria Sainsbury's chapter in Things That Travelled, regarding the reuse of Romano-British glass post-410 CE. These itinerant glass hawkers also appear in a number of classical sources, with Cassius Dio, and I do apologise for any classicists wanting the Latin, this is what you've got today. Cassius Dio relating to us saying that under the Emperor Claudius, a man could become a citizen in exchange for a bit of broken glass. Pliny the Elder also references glass and glass recycling, although he appears to be operating on either out-of-date or completely incorrect information, such as when he asserts that glass can definitely be held together with sulfur. The mixing of a number of different glass vessels via the recycling process can lead to complex geochemical profiles, but the presence of a number of elements in the glass can be used as a simple identifier of Romano-British glass material. Antimony, for example, is not present in quartz or any of the other components of glass in any significant concentration, but there is a significant amount of antimony being added to recycled glass as both an opacifier and a decolorant. Whilst this could be seen as a simplistic silver bullet for the identification of antimony, the concentration of antimony is often highly variable, which means that there's a high possibility that the glass that has been recycled is not detected by materials analysis due to the calibration of the equipment used. And with that, we better go back to our chemistry lesson. So I hope you like diagrams. Not to assume knowledge, but as XRF is fairly commonly used now, especially with more frequent use of handheld XRF in museum and cultural heritage contexts, I'll provide a relatively whistle-stop explanation. Essentially, XRF involves firing a very controlled amount of X-rays at the object or sample. I have a very blocky diagram to have a look at, so you can see what the detector sort of looks like, which will then penetrate the surface of the object/sample. The X-rays then donate energy to the atoms, which then displaces the electrons from the object out of place. This then leads to the atoms giving off their own X-rays. This is the fluorescence in the name, which the equipment then detects. As each element gives off its own unique signature, it's then relatively simple to see what we have going on in the sample. This is a useful technique to identify major and minor elements quickly and non-destructively. A key limitation to this technique is that it often cannot detect trace elements and light elements, such as sodium or magnesium, which can be slightly problematic when dealing with glass analysis. So, we now move on to the catchily named inductively coupled plasma mass spectrometry, or ICP-MS. So, whilst XRF is a valuable form of materials analysis, ICP-MS is a more highly valued for its high sensitivity, accuracy, and ability to detect trace elements at concentrations as low as parts per billion or parts per trillion. This is particularly useful when analysing ancient glass. The sample is introduced into the plasma torch, and I've upgraded the diagram here because it is slightly more complicated, which superheats the sample and ionizes it, which creates a stream of positively charged ions, which can then be passed through a quadrupole, so you can see the 4 poles, which sorts and separates the ions based on their mass to charge ratio. The detector can then quantify the elements in the sample and measure the abundance of each ion, which can then produce elemental concentrations. Unlike XRF, as previously stated, ICP-MS is particularly good for identifying trace elements. But unlike XRF, there is a significant price tag attached to using this specialized equipment. As part of this project, the ICP work I will be conducting in the Durham University Department of Earth Sciences will be funded by both the BINS Fund and the Williams Bursary from University College Durham. It is important to note, and this will be significant later on in the talk, so keep it in the back of your head, that the quality of results generated from this equipment is as much down to the quality of the calibration and usage of the machine as it is down to the preparation and selection of the samples. So, as demonstrated by the diagram I've forced you all to look at, glass is not a crystalline structure and is therefore highly vulnerable to leaching and weather in post-deposition, which can lead to changes in composition, color, and iridescence. As the previous slide discussed, recycling can complicate the composition of the glass vessel, which could lead to weakness in the structure of the glass and lead to an increased likelihood of the glass developing something called glass disease, which is a process of deterioration that leads to the formation of shiny deposits on the surface of glass and will lead to the disintegration of the vessel over time. Whilst glass disease is significant when discussing Romano-British recycled glass, it is a topic that takes slightly too long to discuss within the spawns of this topic. But to surmise, and as hopefully illustrated by the photographs from the Corning Museum glass, having deposits on the surface considerably complicates the process of materials analysis. The process of manufacturing Romano-British glass, and as is the case with all manufacturing really, no matter how much we want to think about it, can be fraught with errors. And as outlined by Sarah Painter, Mark Taylor, and David Hill, this manufacturing method can also lead to the slumping of vessels and the pooling of colorants in the necks or other curved portions of the vessels, which can lead to weaknesses. This pooling of minerals, as well as the large inclusions picked up during the firing and cooling processes, not only causes problems with the structural integrity of the vessels, but also when conducting material analysis from the vessels. As previously discussed, XRF can only penetrate from a few microns to a millimeter of the surface of the object, depending on its matrix, and in one specific area at the time, hence me using the term point-based. With any surface degradation or surface inclusions, this could then create inaccurate results, which makes the selection of samples more complex. The majority of glass studies circumvent this by either intensive sanding or drilling of samples, which can lead to a loss of a large amount of material. Of course, in the case of some objects, it's impossible to avoid these inclusions. By employing the methodology I will outline later in this talk, I hope to counteract this to some extent. So, on to Binchester. Binchester Roman Fort, located in County Durham, England, was an important military outpost in the northern frontier of Britain. Established in the late 1st century, it was strategically positioned along Deer Street, a major Roman road connecting York to Hadrian's Wall. The fort housed cavalry units, and over time an extramural settlement was developed around the fort. Excavations have uncovered well-preserved remains, including bathhouses and barracks. And, luckily for me, there is an abundant amount of glass material available from the Durham University and Durham Archaeological Services excavations from Trenches 1 and 2. It's important to note at this point that Trench 1 represents the material from the barracks, and Trench 2 represents the material from the extramural settlement. As the material is abundant, careful selection of samples was key, both for the practicalities of time and the implications of conducting large-scale destructive analysis. There is a continuous process of cataloguing the glass material from Binchester running at Durham University, where both undergrad and postgraduate students have been measuring and writing short descriptions of the glass fragments. Having selected a box for sampling, I then recorded all of the material in a similar manner, as demonstrated by this not entirely extensive, this is just a very small amount of part of my database, just on the screen grab there. This was also cross-referenced with the Binchester Context Registers, which was kindly provided by Professor Chris Gerard, who, along with Dr. David Petts, provided permission to work with the material from Binchester. From this, I then selected 35 samples based on colour and evenly divided between Trench 1 and 2. I have included some photographs for your enjoyment and to demonstrate the wide variety of material available. Coincidentally, box 15.5, the box I selected, largely contained non-diagnostic fragments, but there were some impressive diagnostic fragments which I photographed that will not be subjecting to destructive analysis for obvious reasons. Having conducted some basic cleaning and photography, which you saw on my first slide and here, I could then begin analysis. So, the process of grinding up samples and forming them into pellets for XRF sampling is a fairly common process within the study of ancient ceramics, but isn't often used as much in glass. So, by grinding the sample down to a very fine powder, the glass sample is effectively homogenized even before the process of analysis has begun. This is achieved through a combination of blunt force and crushing using a ball mill. This fine powder can also be used as is for ICP sampling, as it will either be dissolved in acid or vaporized. XRF requires a solid surface for the X-ray to penetrate, so the powder must be formed into a pellet or bead, which you can see here. As the sample is effectively homogeneous at this point, a very small amount of the powder collected, so only 600 milligrams, is combined with the flux used to make this bead. The mix of powder and flux is then heated to a high temperature, which then forms a flat, clear pellet. The sample is now effectively ready to go for analysis, which is fantastic. Whilst adding flux arguably dilutes the sample, the pellets are used exclusively for XRF, which is designed to detect major elements, whereas the undiluted powder is used for ICP, which is best suited for detecting trace elements, and therefore the concentration is considerably less of an issue. So, by combining these two techniques, we can extract the optimum amount of information about the elemental composition which is further augmented by the sample treatment process. It may also be of interest to note, for anyone who's worried about destructive analysis, that only a gram of each sample is needed, as the remaining 400 milligrams that we have left over from making the pellets can be used for ICP. So it is possible to keep the destructivity of the method relatively low. So in terms of possible outcomes, this analysis of the glass assemblage could reveal the presence of catchily named HIMT glass, which is a yellow-green variety with high concentrations of iron, manganese, and titanium, hence the acronym, typically associated with the 4th century. Levantine 1 glass may also be identified, which is characterized by its bluish-greenish hue, low soda, high lime, and relatively high aluminium contents, which suggests links to 4th century production. Additionally, analysis might indicate the presence of blue-green glass from the 1st to 3rd centuries. I'll give you a reward if you sort of spot any of that in some of my earlier slides, which is distinguishable by similar iron oxide levels, but higher potash and significantly lower titanium concentrations. These potential findings would contribute to understanding of chronological patterns, trade networks, and technological developments in glass production. So, whilst this study is unlikely to unearth any startling new discoveries regarding Romano-British glass production and consumption, my apologies, everyone, terribly sorry, I will be interested to see if there's any improvement in the accuracy of results with the background noise through the new pre-treatment analysis, which I have been outlining in this talk, in comparison with other glass analysis projects, such as Sarah Painter's 2006 study of the colourless glass from the previous round of excavations at Binchester. This study will form a very small part in the much larger pantheon of Romano-British glass analysis. So, to conclude, this paper can be seen as a brief outline of the work I'm currently undertaking as part of my MA dissertation. This methodology, although well used in heavy industry and the study of ceramics, is new to the field of ancient glassware, and the combination of XRF and ICP will hopefully allow me to explore some of the questions I have regarding socioeconomic differences between fort and extramural settlement as part of my MA dissertation, and the potential of glass as proxy for understanding trade in a similar manner to numismatics or Samianware. To quickly finish, I'd like to thank Professor Christopher Gerard and Dr. David Petz for continued access to the Binchester glass and their permission to sample and analyse destructively, and for all those who worked on the Binchester excavations. I'd also like to thank Dr. Kamal Badrashani, my supervisor, for his knowledge and expertise, and Dr. Ellery Cousins for her help and advice in forming what will become my MA dissertation. And very lastly, but not least, I'd like to thank Alex Muggleston, Annie Veum, Millie Durant, and Isabel and Harriet Stockton for their work on cataloguing the vast assemblage from Binchester. As you can see, I've put my contact details up on the final slide, so please feel free to get in touch if you'd like to. I also have an electronic handout if anyone would like to email me for that, which would be lovely. So thank you for listening to me waffle.